So today what we are going to read is we are going to deal with rotational motion, and in rotational motion we'll be dealing with types of motion. We can categorize the types of motion in three ways. First is rectilinear motion. Rectilinear motion. Here the particle just moves in a straight line. For example, say some block is here, say some block of mass in, and that block is moving to different positions like this, as you can see it here. So this particle is performing rectilinear motion in this direction. This is rectilinear motion. Okay, so secondly we'll be dealing with curvilinear motion. Curvilinear motion. Here the particle will move in such a way that it can follow any track of any shape. But say for example some rod is here, and that rod is say like this. This is point A of rod, and there is one more point, say this is point B on rod. This is the rod. Each time the orientation of rod will remain same, it will not change at all. I mean to say that the angle that rod is making is not gonna change anyways. You can see here that AB is a vertical line, this again AB is a vertical line, this AB is again a vertical line, and so on. So in curvilinear motion, the orientation of rod, the orientation of this rod is not changing. Orientation is not changing. So the orientation always remains same. In third kind of type of motion, we can categorize the motion as rotational motion, where so we can say that it is the type of motion where all the particles of object moves in concentric circles of different radii. Here the particles keep on moving in concentric circles of different radii. They keep, for example, you can see it here that there is say some rod is here, and 2 points are in this rod, say A and point B. If this rod is rotating, then after some time the orientation of this rod will be like this, and A and B will be in these positions. After some more time the rod will move to this position. This will be point A, this will be point B. So we can see that the point A moves some angle, then it again moves some angle. Similarly point B covers some angle, and again it moves with some angle. So initially it completed angle θ1, and next to it completed an angle θ2. So this way we can say that the orientation, here we can say that orientation of line, the orientation of line is changing. While in curvilinear motion you can easily see that the orientation of this line is not changing at all. While in this case, the orientation of line is regularly or continuously changing. So this is rotational motion. Next to it, what we'll be dealing with is we'll be dealing with moment of inertia. Now the point arises, what is this moment of inertia actually? So we can say that it is a property, or we can say that it is an analogous property and it plays the same role in rotational motion as being played by mass in translational motion. So I mean to say that we say that if there are two blocks, say one block is of 2 kg and one more block we have, say that is of some heavier mass, say 5 kg, then it will be tough to move this 5 kg block, and it will be easy to move this 2 kg block. Similarly, in rotational motion we can say that if somebody is having high moment of inertia is generally represented by symbol I. It's a tensor quantity. Tensor quantity have some properties that lies between, you can say, vector and scalar, but we are not much bothered about these tensor quantities. So what I mean to say is moment of inertia is generally represented by the symbol I. It's a tensor quantity, and we can define moment of inertia for different kind of objects, like for discrete mass systems and continuous mass systems, that we'll deal later on. For the time being, we should be dealing with SI unit of moment of inertia, which is kg into meter square. Now our major task is to calculate moment of inertia of different objects. So let's start one more topic, calculation of moment of inertia. So as far as moment of inertia is concerned, we have divided all the systems in two categories. First is discrete mass systems. As the name suggests, discrete mass systems mean various masses are present around the axis at different coordinates. Say these masses are rotating about say this axis, then this is r1, mass of this object is m1, the mass of this object is m2, and radius is say r2. For this, mass is m3, radius is r3, and all these objects are rotating about this axis with some omega. Then we can define the moment of inertia of this system as summation of mi ri square. That is, moment of inertia is equal to m1 r1 square, m2 r2 square, and so on up to n turns. You can easily see that the unit of moment of inertia is kg for mass and meter square for radius square. So if we talk of some example, say if I ask you what will be the moment of inertia of this 1 kg object which is at a distance of 1 meter from this axis, and it is rotating about this axis, then you'll say that moment of inertia of this 1 kg object will be mass into radius, that is 1 ka square, and I is equal to 1 for this system of mass. Talking about more complex systems, we generally deal with continuous mass distribution systems. Continuous mass distribution systems. Here mass is present in a regular fashion. Like if I talk about this rod, then mass is present everywhere on this rod. Similarly, if I talk of some ring, then mass is present everywhere on the ring, on the periphery of the ring. So this way we can define continuous mass systems. Now in next section or in next video, we'll be dealing with the calculation of moment of inertia of continuous mass distributions.